This photograph was taken with 2 different telescopes. Hello, astronomy enthusiasts from all over the world. I'm Luis Miguel Azorin, and I welcome you to a new video from Astro Academy. If you regularly follow both Astro Academy and Natural Portraits, you'll know that at the end of April, 2 members of the Astro Academy project traveled to the Atacama Desert in Chile and the Uyuni Salt Flats in Bolivia in search of the best night skies in the world. And from that trip came some truly stunning photographs. If you don't know which trip I'm talking about, I recommend you don't miss the series of 3 special videos we published on the Natural Portraits channel, which perfectly sum up what this adventure was like. One of the best astrophotographs that came out of this trip was this one, the Great Eta Carinae Nebula, the brightest nebula in the southern sky. And what's interesting about this photograph is that it was captured using 2 different telescopes. 1 hour of integration with a NASCAR SQA55, and another hour of integration with a William Optics RedCat 51. We combined the data from both telescopes to obtain a stacked image, which we then processed until we achieved this result. So, how did we do this? In this video, I'm going to explain it to you, but it was actually very simple because both telescopes are very similar in terms of aperture and focal length. But it's also possible to do this with telescopes that are much more different. These and many other topics are covered in the complete beginner courses on PixInsight for color cameras at Academia Natural Portraits, as well as in the Advanced Techniques in PixInsight course at Astro Academy. Almost 20 hours of total training so you can learn to process with PixInsight from the very basics to the most advanced techniques. In the description of this video, you'll find links to both courses which you can purchase separately or as a bundle. That said, let's go straight to the computer and start processing.
As you'll see, it's super easy to carry out this process to combine the images from both telescopes. In fact, PixInsight is an incredibly powerful program that's designed not only to combine images from different telescopes with very similar characteristics like the ones we have in this case, but also to combine images captured by telescopes with very different focal lengths. As I already mentioned, all of this content is included in the PixInsight Advanced Techniques course from Astro Academy. This is a course that you can also complement with the introductory PixInsight course from Academia Natural Portraits. Here we have 2 images open. On the left side we have the image captured by the NASCAR SQA55, and on the right side we have the image captured by the William Optics RedCat 51. As you can see, a lot of attention was paid to the framing. Actually, the framing is not exactly the same. We can see this star here, which appears here in this image. We can also see this orange star here, which we don't have in this image yet, has fallen outside the frame. But overall, the framings are practically identical, especially in terms of rotation angle. I want to emphasize once again that even the rotation angle is not a decisive factor for PixInsight to be able to stack images captured by different telescopes. I have managed to stack images with different focal length and different rotation angles without any issues, but ideally for proper stacking and subsequent processing, the rotation angle and framing should be as similar as possible. Alright, so once we've reviewed this information, the only thing left to do to stack this data is to actually stack it. We go to Script, Batch Processing, Weighted Batch Preprocessing, and here we're going to load all the lights we want to stack at once. Here we have the lights captured by the SQA55, which are these right here. As you can see, 12 lights of 5 minutes each, totaling 1 hour of integration. And we're going to add the lights captured by the William Optics RedCat, which we have right here. Another 12 lights of 300 seconds each. And now we're gonna load the rest of the calibration images, which in this case are just darks. For this image, neither flats nor dark flats were captured, which I have to tell you is not recommended, because among the calibration frames, in my opinion, the most important ones are the flats. However, in this case the sensor was quite clean, the lenses were quite clean, and we didn't observe any vignetting or dust spots in the image that were significant enough to cause a problem, so in the end we didn't capture the flats. But as I said, this is not a recommended practice. With all of this already loaded into weighted batch preprocessing, all you have to do is specify an output directory, which I'm going to set on the desktop. Let's select the highest quality preset here and review the calibration. Here we have 30 dark frames and 24 images of 300 seconds each. After calibration, that's 2 hours of integration. And with all this ready, we simply click Run and then continue. And automatically, PixInsight will start stacking all these captures we've taken, in this case with 2 telescopes, but we could be combining data from 3, 4, 5 or even more telescopes. And here we have the result of this stacking, and as you'll see, it's really interesting. Here is the final integration, which we're going to review now. We have the rejection low, and the rejection high. Let's apply a virtual stretch to each of these images. Take a look at what we have here. We can see the reframing that PixInsight had to do to align both images. As I mentioned, it looked like the same framing, but it actually wasn't. And the rotation angle, as we're seeing, was similar, but there was a significant difference between the two images. This here is the rejection high, and here we have the rejection low, where what I'm telling you is even more evident. Here we can clearly see how in one of the stacks it even cropped a small part of the image in order to align and match it up. And as I mentioned, in this case we're talking about 2 telescopes that are very similar in terms of performance, but in the PixInsight course, Advanced Techniques by Astro Academy, you can see how we carry out this same process with captures taken at very different rotation angles and with different focal lengths. And here we have the final stack. Let's take a look and see how it turned out. Well, just look at what we have here. Here, we don't see any evidence of those cutouts we saw in the rejection high and rejection low. And we're only talking about 1 hour of integration with each of the telescopes. Just imagine if we stack many more hours of integration. Imagine if we stack 4, 5, 6, even 10 hours of integration with each of the telescope as the result we could achieve. If we zoom in, we can see that we have perfect stars, and there's no sign of halos in any of the corners or at any of the edges of the image. We really have a perfectly stacked image ready to start processing. From this point on, all that's left is processing until we achieve a fully finished image. Alright, so next what we're going to do is go through a basic processing workflow that I would apply to this astrophotograph. However, as I mentioned, if you want to explore much more advanced techniques than what I'm going to show you in this video, I recommend you check out the courses from Academia Natural Portraits and Astro Academy. The first thing I'm going to do is check that there are indeed no poorly stacked edges in the photograph. Even though we've already taken a look, well, I don't see any edges that need to be cropped in this particular astrophotograph, despite the fact that, as we've seen, a significant crop was applied to the images captured by one of the telescopes. But in principle, the edges of this image are very good, so we are not going to use the dynamic crop tool. We are going to go directly to the gradient correction tool, because even though the image is quite flat, we can see that this part here on the left is slightly brighter, and we can easily correct this from all processes, gradient correction. We are going to apply this tool with the default parameters, which will work very well, and there we have the correction already applied. This is before and after. As you can see, there was indeed a slight gradient in the photo, which we have now completely corrected. The next step is to perform color calibration on this image, and for this, there is no better way than to use PixInsight's own database and let it handle the color calibration of this particular object. This object is specifically NGC 3372, the Eta Carinae Nebula. So the first thing we're going to do is go to Script, Astrometry, Image Solver, and we're going to tell it that we're photographing the object NGC 3372. We select the object and click OK, making sure that all the data shown here, especially the focal length, resolution and pixel size, match the specifications of the equipment we've used. Then we click OK. Alright, we've now completed the plate solving, and PixInsight knows exactly which part of the sky we've photographed. So now we can go to the spectrophotometric color calibration process, where we'll specify the type of sensor we've used and the type of filter we've applied. In this case, it's a color sensor, so we're going to use Sony Color Sensor RGB with an infrared and ultraviolet cut filter. So with the tool configured this way, I apply it to the image and wait for PixInsight to perform the color calibration, paying attention to that plate solving we just did a moment ago. Basically, PixInsight is calibrating the color specifically for this nebula. Alright, now the color calibration is done. Here we have the graphs with all the information from the color calibration that was performed. We can close this now. And notice that now we have a rather blue image. Well, we shouldn't trust this just yet. How can we know if the color calibration has actually been applied correctly? Well, for that, we're going to activate the little chain so that each of the 3 RGB channels is stretched equally, and then we'll click the radioactive symbol take and look at what we get. By stretching all 3 channels equally, we get a perfectly neutral image. Therefore, the color calibration has been correctly applied to our image. I can now close spectrophotometric color calibration, and the next step will be to apply a deconvolution. And the best tool I know for deconvolution is Blur Exterminator. As you know, it's a paid tool, but it works incredibly well. I have it here, Blur Exterminator, and we're going to apply it to a preview by pressing Alt+N. I'm going to capture a preview of, for example, this area of the image where we have sky background, where we have the brightest parts of the nebula, and let's see how the Blur Exterminator tool works. I'm going to apply it with the default parameters it gives me. I enable a real-time view, and here we already have the preview of the deconvolution on our preview area. If I toggle it on and off, look at the incredible difference. On one hand, the stars, which are already very well defined in this image, become much smaller and sharper. On the other hand, the nebula in this case, this dark nebulae we have in the center of the image, look at what happens when we activate it. They become much more defined. This deconvolution is correct. I close the preview and apply it to the entire image. There we have our image with the deconvolution applied. I'm going to close the preview, and with this we've practically completed 100% of the linear processing of our image. Notice that it's been 4 super quick and super simple steps, and now our image is ready for histogram stretching, that is, the transition from linear processing to non-linear processing. What I'm going to do is close the Blur Exterminator tool, and we're going to move on to histogram stretching. For this, the first thing I'm going to do is reset the screen transfer function tool, because from now on we're going to stretch the photograph. And how do I like to stretch my Astro photographs so that they look super natural and capture as much information as possible? Well, I always use the Generalized Hyperbolic Stretch tool, which is a super powerful histogram stretching tool. So how do I use this tool? Well, this tool is one that you apply iteratively. That is, we're not going to apply a single stretch to our image, but instead we'll apply a series of small stretches until we achieve exactly the level of histogram stretching we want. The first thing I always do is trim the shadows. Notice that here we have the entire histogram pyramid, and on the left side we have quite a large margin of shadows. Alright, let's trim those shadows. To do this, I go here to Transformation Type, set it to Linear Mode, right click where I want to cut, which in this case would be roughly here, and select Send to BP, Black Point, which we have right here. Once that's done, I apply it to the image. Now we've trimmed the shadow area. Next, let's move on to stretching the histogram. I click here, always on the histogram pyramid, slightly to the right, and here, in this case, we select Send to SP, in Generalized Hyperbolic Mode. This here means sending to the symmetry point. With this step done, I can now switch to a more general view of the histogram, and I'll start gradually lifting it, always using the real-time preview. I'm going to keep gradually lifting it, always compensating for highlight protection and also raising the local intensity slider. Notice how we're making small incremental adjustments. This would be a first step. Alright, let's apply it to the image. There it is. Now we're gonna repeat the process, directly lifting the histogram and sending it to the symmetry point. I right click here, send it to the symmetry point, and apply the process again. I raise the stretch factor a little, local intensity, protect the highlights a bit, and apply. And we'll keep doing this excessively until we achieve a satisfactory stretch. Well, with this, I think the histogram is sufficiently stretched. Look at the incredible signal this nebula gives us. We now have a perfect histogram, so as far as I'm concerned, the photo is already stretched. So I'm going to close the Generalized Hyperbolic Stretch tool. I'll also close the Screen Transfer function since I don't need it anymore. And now comes the most creative part of astrophotography processing, which is the nonlinear stage. Throughout my journey in astrophotography, I've slightly changed my process, and today I find that the best way to process a color image like the one we have here is to separate the stars from the background, process both separately, and finally in the last step, merge them. How am I going to do this? Well, I'm going to resort to that. First, I'm going to apply an SCNR noise reduction to remove any green color cast that might be present in the photo, because in astrophotography, green except in comets is considered noise. So, I apply this tool. Alright, I don't notice any green cast, at least nothing too pronounced. I'll close this, and now let's separate the stars from the background. I'm going to use the StarNet tool. I'll tell it to create a star mask for me, and let's apply it. Alright, here we have it. I'll close this now. And here are the stars. Just look at the sheer number of stars in this image. I'll minimize them and leave them here. And here we have the nebulosity, which is also truly amazing. We're going to work directly on the nebulosity. Let's enhance everything we have here. And a tool I love for enhancing all of these is the exponential transformation tool we have here. Notice how it allows me to bring up the light in the entire photo in a super precise and powerful way. We apply this tool, and now we're going to keep working on the weaker nebulosity. For this, I'm going to create a mask. Let's extract a luminance. We're going to work a bit on that luminance with histogram transformation and try to enhance all those nebulosity features. Something like that. We apply, and now we're going to apply a slight convolution to soften the mask. Something like this. And finally, we apply the mask to the image. There we have it. Alright, now I'm going to start working with the curves. I go to Process or Processes, Curves, Transformation. And we are going to start working on those weaker structures that are in the background of the sky. Okay, something like that. I'm going to apply another mask, and in this case, I'm going to create a range mask. First, I'm going to extract the luminance. I will go back to working a little bit more on that luminance with the histogram. There it is. I want a lot of truly significant, very detailed, and comprehensive information. And now, we're going to create a range mask. For this, I go to Process or Processes, Range Selection. And here, I can work directly on this mask to, on one hand, protect the brightest areas, and on the other hand, manage to isolate those weaker nebulosities we have in the background. Let me remind you once again that all of this is covered in great detail in the courses at Academia Natural Portraits and Astro Academy. Alright, that's more or less where we want it. We apply it to the image, and now we apply this mask to the image of the sky background. And in this case, we really need to be very subtle, because it's a somewhat harsh mask, and otherwise things can end up looking quite artificial. But if we're subtle, we can still bring out even more of all that information that's in the background of the image. Something like this would be perfect for me. Now we remove all these masks, and what I'm going to do is give the color a boost. Without any kind of mask, I come here to Curve Transformation, activate the chrominance curve, and look at how all the colors come out. The amount of color we have here is just incredible. In fact, we have to be careful because it's very easy to go overboard. There we have it. Perfect. From this point on, the background is already processed, it's just how I want it. What I'm going to do now is work on the stars. And the first thing I'm going to do is apply a star reduction directly on the star mask I have here. For this, I go to a super powerful script I have here in Script Utilities, which is Star Reduction. This script requires us to have a starless image, a starless view. So what I'm going to do is tell it to generate one for me automatically. I click here, and it would generate it for me with StarNet. Execute. Alright, here we already have the starless image it just generated for us, and notice how applying it directly already reduces the stars a lot. In fact, we have several star reduction modes in this script. In this case, I have the lightness method applied, which is the newest one in this script, the soft mode, and in this case, 2 iterations, because we have a lot of stars. And I think with this significant star reduction is looking pretty good, so I'm going to proceed and click the prominent green check mark. And now, as you can clearly see, we have successfully achieved our desired star reduction. Notice the distinct and noticeable difference between the original, unedited stars and the newly reduced, refined stars. Anyway, I'll just minimize all of this for now and move on to recombining the background and the stars. I'm gonna do this with the Pixel Math tool, where I'll simply apply an addition. I'll tell it to take the integration, plus the carefully reduced stars image, and we will then apply all of this information to the background of the image. And here we have our photo again, now with that enhanced background we've applied, and with those reduced stars that we've directly minimized using the star mask we had. And just look at the result we've achieved. Honestly, it's a really powerful result.
As you can clearly see, this time we have meticulously prepared and brought to you a video presentation that is distinctly different from our usual content. It is considerably much longer in duration, offering an extended viewing experience, and is far more specific in its detailed focus, delving deeply into particular aspects and providing an in-depth exploration of its subject matter. But let me remind you that you can build on everything you've just seen with the full courses you'll find at Astro Academy and at Academia Natural Portraits. I'll see you again in the next video from Astro Academy.